Good day, future engineers. Welcome to another session of learning more about chemistry. Today, we will be discussing about chemical bonding and geometry of molecules. Let's begin our discussion with getting to know more about the main focus of this discussion. What is chemical bonding? Chemical bond is described as the forces that hold oppositely charged ions together or hold atoms together in molecules. It also involves changes in electronic configuration for the atoms to be stable. Chemical bond is characterized by the formation of octets. So why do atoms bind? The simple answer is stability. For us to be guided in our discussion, let us try to recall some of the important terminologies we will encounter as we go on with our lesson. Metal is electron donor to attain stability, while non-metal electron acceptor to complete the atom's outermost shell. Noble gas, neither an electron donor nor an electron acceptor. And valence electron, electron in the outer energy level of an atom. To start with, let us try to see how atoms achieve stability. Stability is achieved via the alteration in the electronic configuration, and there are three possible ways. First, metals donate electrons to attain stability. Nonmetals, on the other hand, can accept electrons to complete the atom's outermost shell. But nonmetals can also share electrons with each other. This alteration results to chemical bonding. What are the types of chemical bonding? There are two types of chemical bond, which are ionic bond and covalent bond. Let's deal with ionic bond first. Ionic bond is an electrovalent bond that happens when atoms donate electrons to attain stability. It is formed from electrostatic attraction between oppositely charged ions having positive and negative. Ionic bond is said to be characterized by the formation of true octet, since electrons of one atom are transferred permanently. Looking at this example, electron is given away by the cation, while the anion on the other hand accept the electron, just like how the compound lithium fluoride is formed. On this part of the lesson, let us discuss covalent bond. It is known as the interatomic linkage that results from the sharing of an electron pair. For covalent bonds, the binding arises from the electrostatic attraction of their nuclei for the same electrons. Covalent bonds are more complex compared with ionic bond. There are two types of covalent bond which are known as nonpolar and polar. What is a nonpolar covalent bond? This occurs when atoms equally share electron pairs. This is the bond between two atoms with the same electronegativity value. The most common example is diatomic molecules. Hydrogen gas is formed by the bond between atoms, which is connected by a single bond through its valence electrons. On the other hand, bromine has 7 valence electrons that when it binds with another bromine atom, a single bond is formed to achieve octet. Lastly, oxygen gas is formed through a double bond formed from the 6 valence electrons. On this part, we will also be discussing polar covalent bond. This is characterized by the shared electrons between atoms which are not equal. It occurs when one atom has a higher electronegativity than the other atom. Some examples include hydrogen fluoride, hydrogen chloride or your hydrochloric acid, hydrogen bromide, and hydrogen iodide. Taking a look at this diagram, the electronegativity difference results to having a dipole moment wherein the less electronegative side takes the partially positive sign, while the more electronegative side takes the partially negative sign. In this diagram, they are represented as the electron densities, thus having electron poor and electron rich regions. Electron poor, electron rich regions. As seen in this example, there is an unequal sharing of electrons. As you can see here in the hydrogen fluoride, hydrogen bromide, hydrogen iodide, and your hydrochloric acid. Let us continue with our discussion as we get to know the three types of covalent bonds, which are known as the single bond, double, and triple bonds. A single bond is characterized by two electrons that are shared between two atoms or having two atoms sharing one pair of electrons in their bond. On the other hand, a double bond is having two atoms sharing two pairs of electrons in each other. Lastly, a triple bond is having three pairs of electrons that are shared between two atoms in a molecule. How are these bonds represented? The representation of bonds is through the Lewis electron dot structure, other known as LEDs. It is a type of shorthand notation. Apart from the other types such as empirical formula, molecular formula, and others, LEDs have lines between atoms to indicate chemical bonds, and thus to show unbonded electrons. There are two imperative things to consider for LEDs, which are the valence electrons and the octet rule. What is octet rule? Octet rule requires all atoms in a molecule to have 8 valence electrons to become stable. Stability is achieved by sharing, losing, or gaining electrons. How do we write the Lewis electron dot structure? The first step is picking the central atom. Compare the atoms involved in the compound, and the one with the lowest electronegativity is usually considered as central atom. For example, we have nitrogen trifluoride. Let's recall electronegativity from periodic trends. Based on the trend, the central atom then is nitrogen since it has lower electronegativity compared to fluorine, given by the pattern En increasing across period. The next step is counting the electrons. By electrons, we mean that valence electrons since they are the ones involved in chemical bonding. We take the total number of valence electrons from each of atom for polyatomic compounds that carry charges. For polyatomic anions, add the number of negative charges to the total, while for polyatomic cations, subtract the number of positive charges from the total. In this example, nitrogen has 5 valence electrons. On the other hand, fluorine has 7 valence electrons. And since we have 3 fluorine atoms, we multiply it with 3, so it will give us the total of 21 electrons. In total, we then have 26 valence electrons to distribute. We will now try to distribute the electrons. Since nitrogen is the central atom, we will be placing it in the middle. We'll then form single bonds, first for each of the atom of fluorine. Having done that, we will distribute the remaining electrons. From the 3 pairs of bonds, we already have 6 electrons, thus we have 20 more to distribute. Giving each fluorine 6 electrons, we will have 18 electrons. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, and 6. The 2 more electrons to nitrogen. 1, 2. Remember to allocate the number of electrons based on the original valence. The last step is to confirm the stability by checking the octet. Let's count if each atom already has 8 electrons in their valence. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and the lone pair of nitrogen. So as you can see here, there are 8 valence electrons, 8 valence electrons, 8 valence electrons, and of course the nitrogen, it has 8 valence electrons. Okay, how is stability further confirmed? The concept of formal charge verifies stability. Formal charge is known as the hypothetical charge of the atom. The sum of the formal charge of each atom will be the formal charge of the compound. So there are 2 things to consider, which are the non-bonding electrons, which are known as the lone pairs when counted by pair, and the bonding electron, which are the electrons involved in the bonding. 2 electrons form 1 bonding pair. How do we compute the formal charge? Formal charge is equal to the valence electrons minus the bonding pairs minus the non-bonding electrons. This is represented by Fc is equal to Ve minus Bp minus Nbe. Let's have an example. For ozone, we will have to compute the formal charge of each atom. For oxygen 1, the formal charge is equal to the valence electrons, which is 6, minus the bonding pair, which is 3, minus the non-bonding electrons, which is 2. The 6 minus 3 minus 2 is positive 1. For our oxygen 2, the formal charge is equal to the valence electrons, which is 6, minus the 2 bonding pair, minus the 4 non-bonding electrons. The 6 minus 2 minus 4 is equal to 0. And for our oxygen 3, the formal charge is equal to the valence electrons, which is 6, minus the 1 bonding pair, and of course minus the 6 non-bonding electrons. So 6 minus 1 minus 6 is equal to negative 1. Thus, the formal charge of ozone is equal to positive 1 plus 0 plus negative 1, which is equal to 0. Thus, the formal charge of ozone is 0. Okay? That's it for today. I hope you learned from our discussion. See you again next time. God bless.